Hello and welcome to the Daily Space. My name is Pamela Gay and I'm sitting in for Annie Wilson while she takes a well deserved day off. Most weekdays, the CosmoQuest team is here putting science in your brain. Today, however, is for Rocket Roundup. Let's get to it, shall we? This week was a light week as far as rocket launches go. No rockets were launched to orbit. The one and only rocket that did take off was NS-15, Blue Origin's New Shepard, on a surprise mission at 1750 UTC on April 14th. When I say surprise, I don't mean that the launch was a secret, but rather that they only announced that it would occur 3 days before the launch. Usually there are more notices for rocket launches, like weeks or months ahead. It may not be an exact date, and dates do change, but most of the time it's known what rocket is expected to take off when. Again, dates do change. And this is how you end up planning a trip to see rocket launches and then don't see any rocket launches. Anyways, Blue Origin didn't say anything until a Twitter bot called Space TFRs posted that there was a filing for an airspace closure over Blue Origin's launch site in Corn Ranch, Texas. Even after that tweet, it took almost 6 hours for Blue Origin to put out an official tweet promising more details soon. All of this is in stark contrast to SpaceX's Starship program, which is conducted largely in the open. On the day of launch, the Blue Origin webcast went live about an hour before their intended launch time. After over an hour of delays, the vehicle lifted off into the clear blue West Texas sky. The launch was nominal, and about 10 minutes after launch, both the booster and capsule successfully landed back on the ground. The booster reached an apogee or highest point of 105 kilometers above ground level. The capsule reached a slightly higher apogee of 107 kilometers. Total mission elapsed time was just over 10 minutes, and the peak velocity of the capsule was just under 1 kilometer a second. NS-15 is the latest in Blue Origin's test program of the New Shepard vehicle, and Blue Origin described it as a verification step prior to flying crew. During the countdown, 4 astronaut stand-in employees practiced getting into the white room on the launch tower and boarding the capsule as the rocket was fully fueled. 2 of the stand-in astronauts were strapped into the seats and the hatch closed. The hatch wasn't closed for long, though, and the stand-in astronauts were swiftly removed and replaced by a dummy astronaut called Mannequin Skywalker. Then, the hatch was securely fastened and the rocket was launched. After the capsule landed, the stand-in astronauts got back in the capsule and the recovery crew practiced taking the astronauts out of the capsule as if they had landed in it, with the recovery crew opening the hatch and assisting the astronauts out of their seats. Other payloads on the capsule included the, as we said, instrumented test dummy Mannequin Skywalker and 25,000 postcards from students in Blue Origin's Club for the Future. Let's take a look at the launch and the subsequent landings of the rocket and capsule.
T-minus 10, 9, 8, 7, 6, 5, 4. Command engine start. 2, 1.
And we have liftoff. Go, New Shepard, go. Beautiful liftoff from our launch site 1 in West Texas. You can follow along as she gains speed in the bottom left corner of your screen. There's the speedometer, altimeter in the middle there. All right, there go the drag brakes. And there you see all the speed bleeding off of the vehicle and waiting for our BE-3 engine to relight. There it goes. Landing gear deployed. Oh, look at that smooth landing. And touchdown. Welcome back, New Shepard.
Oh my God, what a beautiful landing,
I think
right?
that was one of the smooth. And here come the mains. All 3 parachutes are out. We're looking for full inflation, and there they go. I love that. So far, so good. A nominal launch, nominal landing for the booster. We're waiting for the crew capsule to come into land. We're at about 1,600 feet to go. And a nice smooth descent at about 16 or so miles per hour. Just at about 25 or so kilometers per hour. That is a nice smooth descent. There's the valley of our West Texas launch Site 1 as we call it. What a day so far, Patrick, let me tell you.
Another notable event that happened this week was the return of Soyuz MS-17 spacecraft to Earth with the 2 Sergeys, Ryzhov and Kozmirkov, and NASA's Kate Rubin. The 3 boarded their Soyuz spacecraft and undocked from the station at 0134 UTC on April 17th. After several orbits gaining distance from the International Space Station, Soyuz MS-17 conducted its deorbit burn at 0401 UTC. The nearly 5-minute burn imparted a retrograde velocity change of 128 meters per second, just enough to pull the spacecraft back to Earth and land at the primary landing site of Jezkazgan in Kazakhstan, some 54 minutes later. Landing was during the late morning local time, and the Roscosmos recovery team tracked the descending capsule from parachute deployment to the ground. The 3 returning astronauts were then helped out of the capsule into a waiting medical tent. After the checkup, the cosmonauts headed back to Moscow, and Kate started her way back to Houston on a NASA jet. While not exactly a rocket launch, there is one final event we need to mention. On April 19th at 0734 UTC, NASA Mars helicopter Ingenuity successfully performed the first ever powered flight from the surface of another planet. It was a relatively short flight, going to only 3 meters above the surface and having a flight time of just over 39 seconds. But it made history. The flight was completely autonomous because the light speed time delay between Earth and Mars prevents any attempt at the real-time flying of anything. It was made even more challenging by Mars' very thin atmosphere. The atmosphere is so thin, in fact, that it was like the 2 1.2 meter rotors were working at an altitude of 35,000 meters here on Earth. Ingenuity is a technology demonstration, so expectations were very low. This little helicopter demonstrates many commercial off-the-shelf components, mainly from smartphones. Up to 4 more flights of Ingenuity are planned in the coming months, with more ambitious goals than this first flight. After the break, we're going to take a look at how satellites look at Earth. Stay tuned. Remote sensing is a technical term that basically means looking at something from far above it. In the early days, it meant taking pictures with a camera from a kite or balloon, a camera like the one shown here that flew under a balloon. As technology advanced, the kites and balloons were replaced with airplanes, and the cameras became more sophisticated. The airplanes allowed the photographs to be taken from much higher up than the balloons, like the one shown here, or kites could reach, meaning that the field of view of the photographs were wider. As the technology continued to advance, the airplanes were able to reach even higher altitudes, travel farther, and carry even more sophisticated cameras. These were used in wartime. The image shown here shows Anderson aerial camera attached to the side of a Martinsdale G-100 biplane in what was then known as the Ottoman Empire. And not too long after the first artificial satellite Sputnik went beeping into orbit around the Earth, we started putting cameras in satellites to take pictures of the Earth from space. Some of these cameras were not that different from the cameras used at the time for television. But others, they still used film. The satellites using film were able to take much higher resolution images than the electronic cameras could, leading them to be used for intelligence gathering, so many people just refer to them as spysats. Getting the electronic images down from the satellite is a fairly straightforward process. The satellite just transmits the image and a receiving station records it on tape to be processed later. Getting the film back from spysats, however, that was a little more complicated. Once the film, which could be thousands of feet long, was exposed, the satellite transferred it into a return capsule that would be ejected from the satellite at just the right time. After separation from the satellite, the return capsule would fire a small rocket motor to send it back to Earth. Once it was through reentry, the capsule would deploy a parachute, and an airplane towing a hook would recover it. This image is a diagram showing how the Corona satellites would return their film capsules. The US stopped using film capsules to return the images after the last launch of a hexagon satellite in 1986, while the last Russian film return satellite, a Cobalt M satellite, was in 2015. Digital camera technology allowed this aerial recovery procedure to be abandoned because it was now possible to obtain high-resolution images in near real time from virtually anywhere in the world. Originally, highly classified, commercial satellite imagery started to become available, albeit at lower resolutions than the spy satellites could produce, and the uses of it expanded from monitoring what the enemy was doing to things like land use monitoring, crop health, and environmental monitoring. Things like oil spills from leaky ships could easily be identified using satellite imagery. But before you get the impression that remote sensing is just about taking photographs, I should mention that it also encompasses radar sensors that use radio waves rather than the light of the sun. Synthetic aperture radar can penetrate clouds, which are the bane of optical remote sensing satellites, and can also be taken at night, which effectively doubles the opportunities to image something. This is a relief map of North America with height as color taken by the C-band radar on the Shuttle radar topography mission. A few days ago, the European Space Agency posted an article on their website talking about the biggest update to Google Earth since 2017. This update involves a collaboration between Google Earth, the European Space Agency, the European Commission, NASA, and the US Geological Survey. And it makes 24 million satellite photos spanning the last 37 years available. This feature, which is called time-lapse, will allow users to match the changes that have occurred over almost 4 decades. They will be able to see the expansion of cities, the changes to coastlines, and the loss of forests, all of which can be watched by anyone with a browser or a smartphone. We will be bringing you a review of this software on Friday. And what does the future hold for remote sensing? Regular viewers will have heard us report on the launches of new remote sensing satellites. New satellites can be smaller and thus less expensive to build and launch compared to older remote sensing satellites, making the ability to operate a remote sensing satellite much more accessible to small companies and researchers. As more and more of these satellites are launched, access to relatively inexpensive real-time imagery will make them increasingly affordable to use. New satellites will also offer higher resolution imagery, which means you'll be able to make out smaller details in the images. You probably won't be able to read a license plate from space, but you will be able to make a fairly good guess as to what kind of car it is and what color the car is. In this rendering of an icy synthetic aperture radar satellite, we can see one of the many companies making small, synthetic aperture radar missions. We'll put links with more information about remote sensing in the show notes on our website, dailyspace.org. While telescopes are awesome for looking at Earth, they are somewhat more amazing for looking out. After the break, we're going to take a look at the most famous space telescope of all time. Welcome back. This week in rocket history, we're going back 31 years to one of the most important missions of the Space Shuttle program. On April 24th, 1990, at 12:33 UTC, the Space Shuttle Discovery launched from the Kennedy Space Center in Florida. It was crewed by Lauren Shriver, Charles Baldwin Jr., Bruce McCandless, Stephen Hawley, and Catherine Sullivan. This was the 35th Space Shuttle mission, and it was titled STS-31. Let's take a look at that classic launch. Discovery went up to an altitude of around 617 kilometers, the highest orbit ever achieved by any space shuttle mission at that point. The next day, astronaut Stephen Hawley took control of the Remote Manipulation System, also known as RMS or the Canadarm, and used it to pull their primary cargo out of the cargo bay and into space. And thus began the still continuing mission of the Hubble Space Telescope. The 13-meter-long space telescope then deployed its antennas and was supposed to deploy and unfurl its solar arrays, except for one of the solar arrays failed to unfurl. This was a huge problem, since Hubble's batteries could only keep it alive for a couple of hours with only one solar panel extended. If it couldn't be extended in time, an extravehicular activity or EVA had to be performed in order to deploy the array manually. The crew of Discovery was ready for such contingency, as astronauts McCandless and Sullivan were already suited up in their EVA suits and ready with repair kits and tools. McCandless thought the problem was in the software responsible for deploying the solar array and preventing it from overextending. Moments before they would have exited the airlock, an engineer on the ground confirmed McCandless' theory and found a workaround, which allowed the second solar array to be unfurled all the way. Unfortunately for McCandless and Sullivan, this meant they didn't get to observe the deployment of the Space Telescope in person from outside the Space Shuttle. After the Space Telescope was successfully deployed with both solar panels functioning properly, Discovery lowered its orbit slightly and continued its secondary mission, a series of experiments mostly relating to radiation, taking advantage of the high altitude they were in. Discovery landed safely on April 29, 1990 at the Edwards Air Force Base in California. But Hubble's story, that was just beginning. In early May of 1990, the first images started coming down from the telescope, and as many of you probably know, they weren't great. Granted, they were still better than anything taken by ground telescopes, but It was nowhere near the level of detail and clarity the engineers were expecting to receive. It was clear that something had gone wrong with the $4.7 billion telescope. It was later discovered that the company responsible for manufacturing one of Hubble's mirrors had a misaligned measurement unit called a reflective null corrector, which caused them to carve the mirror with the wrong curvature by 2,200 nanometers, which may be only 40 times thinner than a human hair, but was nonetheless enough to cause 1.7 waves of spherical aberration. This is severe enough to affect image clarity. It would be 3 more years and several more billions of dollars before the first servicing mission would go up and a device functioning basically as a pair of glasses would be installed on Hubble and turn it into one of the most prolific and recognizable scientific instruments to date. But that's a story for another time. For now, let's go to commercial. And when we come back, we'll have this week's stats and space fact. Stay tuned. To wrap things up, here's a running tally of a few spaceflight statistics for the current year. Toilets currently in space, 5. 3 installed on ISS, 1 on Crew Dragon, and 1 on Soyuz. Total 2021 orbital launch attempts, 30, including 1 failure. Total satellites from launches, 751. We keep track of orbital launches by where they launched from, also known as spaceport. Here's that breakdown. USA 12, China 9, Kazakhstan 4, New Zealand 2, Russia 2, India 1. Your random space fact for this week is about geocaching. As you can imagine, the vast majority of geocaches are on the Earth. But did you know that there's a geocache on the International Space Station? If you happen to visit the ISS, maybe you can log geocache GE1BE91. This has been The Daily Space.